Look into the darkest space between the stars, and it seems like there is nothing there. No planet, no flame, no visible dust, only a perfect blackness waiting between distant points of light. But modern physics tells a stranger story. The vacuum of space is not truly empty. It is a restless, invisible arena where fields fluctuate, particles can briefly appear, and the structure of reality itself may be hiding in the silence. Today, we are going to explore what empty space really means, why a vacuum can possess energy, and how tiny quantum effects can influence objects across the cosmos. This is not science fiction. It is one of the deepest consequences of quantum theory. To understand the vacuum, we first need to separate everyday emptiness from physical emptiness. A room with no furniture is still filled with air. A chamber with the air pumped out still contains radiation, stray atoms, and a faint glow of thermal energy. Even the best laboratory vacuum is not absolutely empty. But suppose we could remove every atom, every photon, and every speck of dust. Would we finally reach nothing? According to quantum mechanics, we still would not. The reason is that the universe is built from fields. There is an electromagnetic field, an electron field, quark fields, and fields associated with every known particle. What we call a particle is a localized excitation, a small wave or disturbance in one of these fields. The vacuum is the lowest energy state of all those fields. Lowest energy does not mean zero activity. Quantum fields cannot be perfectly still because nature limits how precisely certain pairs of properties can be known at the same time. This is the uncertainty principle. It is often described as a limit on measuring position and momentum, but the same logic applies to fields and their rates of change. A field that was exactly zero, with exactly zero motion, would violate the basic rules of quantum physics. So every field has a residual jitter. These are called vacuum fluctuations. They are not ordinary particles flying around like invisible dust. They are changes in the underlying fields, permitted by quantum theory even in the lowest energy state. A useful image is the surface of an ocean at night. From far away it may look perfectly smooth, but close up, waves and ripples are always moving. The quantum vacuum is stranger still, the ocean is not sitting inside space. It is part of what space physically is. Physicists sometimes describe these fluctuations using virtual particles. The phrase is useful, but it can also mislead. Virtual particles are mathematical contributions inside calculations, not tiny objects that can always be photographed or collected. What matters is that the fluctuations have measurable consequences. One of the clearest examples is the Casimir effect, predicted in the 20th century and later measured in laboratories. Imagine placing two uncharged, conducting plates extremely close together in a vacuum. At first glance, nothing should push them. There is no air pressure between the plates and no electric charge pulling them together. Yet the plates experience a tiny attractive force. The electromagnetic field between them can support only certain wavelengths, while the field outside can support many more. That difference in allowed modes creates a pressure that nudges the plates together. The force is incredibly small at ordinary distances, but it grows rapidly as the gap shrinks. In carefully controlled experiments, the effect can be measured. Empty space, in this case, behaves as though it has structure and pressure. The vacuum can also modify the behavior of atoms. An excited atom does not emit light in complete isolation from its surroundings. It interacts with the electromagnetic field around it, and even the field's lowest energy state can influence the timing and pattern of emission. This helps explain why excited atoms decay and why their energy levels shift by tiny amounts. The Lamb shift, observed in hydrogen, is one celebrated example. Quantum fluctuations slightly alter the energy of atomic states. If the vacuum can affect plates and atoms, could it affect the universe on its largest scales? This question leads to one of cosmology's most difficult mysteries, dark energy. In the late 1990s, observations of distant supernovae revealed that the expansion of the universe is accelerating. Galaxies are not simply moving apart after an ancient explosion. On the largest scales, the expansion itself is speeding up. The simplest explanation is a property of space that produces a persistent outward effect. We call it dark energy. One possibility is that dark energy is the energy of the vacuum, built into space wherever space exists. This idea is appealing because a vacuum energy would remain nearly constant as the universe expands. New space would come with the same energy density, allowing the effect to persist across cosmic time. But there is a spectacular problem. When physicists estimate vacuum energy using straightforward quantum field calculations, the result is vastly larger than the dark energy density inferred from cosmological observations. The mismatch is not a small error. It is among the most extreme discrepancies in theoretical physics. Something must be missing from our understanding. Perhaps quantum contributions cancel in a subtle way. Perhaps gravity responds to vacuum energy differently from other forces. Or perhaps what we call dark energy is a new field with a behavior that only resembles vacuum energy. This uncertainty is why empty space remains an active research frontier. The vacuum is where quantum theory, gravity, and cosmology meet, and those three descriptions of nature do not yet fit together perfectly. There is another surprising consequence. In quantum field theory, particles and forces are defined relative to the vacuum. Change the vacuum state, and the behavior of matter can change with it. The early universe may have passed through several vacuum transitions as it cooled. During those transitions, fields settled into lower energy arrangements, and the forces and particles we know today emerged from a more symmetric primordial state. The Higgs field is a famous example. It fills all of space, and its non-zero background value allows elementary particles such as electrons and quarks to have mass. In that sense, the vacuum is not merely a passive emptiness. It is the environment that gives the particle world its properties. Even black holes are connected to the vacuum. Near an event horizon, the distinction between empty space and observable particles becomes dependent on how an observer moves through spacetime. Quantum field theory in curved spacetime predicts that black holes can emit Hawking radiation. The process is often explained with particle pairs, but the deeper description involves how the vacuum modes are defined on a changing gravitational background. The result is astonishing: a black hole is not perfectly black. Over unimaginable timescales, it can lose energy and eventually evaporate. The quantum behavior of empty space helps transform a one-way cosmic trap into a slowly glowing object. Vacuum fluctuations may also have played a role during cosmic inflation, the proposed period of extraordinarily rapid expansion in the universe's first moments. Tiny quantum variations could have been stretched to astronomical scales. Those variations would later become the seeds of galaxies, clusters, and the great web of cosmic structure. The pattern of matter across billions of light-years may therefore preserve a fossil record of microscopic fluctuations in the early vacuum. From a quantum ripple to a galaxy, the scale difference is almost impossible to imagine. Yet cosmic expansion can magnify a minute fluctuation until it becomes a measurable variation in density. This does not mean the vacuum is a hidden reservoir of free energy that we can easily exploit. Extracting energy from a system in its lowest state is not like opening a battery. The vacuum is the reference state against which other energies are defined. The practical challenge is one reason quantum vacuum effects remain subtle. We can compare different configurations, constrain fields with plates, or observe how atoms respond. But measuring an absolute zero of energy is far harder, especially when gravity is involved. And there is an important philosophical lesson here. In daily language, nothing means the absence of everything. In physics, nothing may mean the simplest state allowed by the laws of nature, and that state can still contain fluctuations, correlations, and consequences. Space is not a box that contains the universe. Space is a physical participant. Its geometry can bend, its expansion can accelerate, and its quantum fields can tremble even when no ordinary particle is present. The next generation of experiments will look for sharper tests. Precision measurements of atomic clocks, nanoscale forces, particle collisions, gravitational waves, and the expansion history of the universe may reveal whether our current picture of the vacuum is complete. Researchers are also searching for clues in the behavior of dark energy. If its strength changes over time, that would point away from a simple cosmological constant and toward a dynamical field. If it remains perfectly constant, the mystery becomes even more precise, not less. The deepest theories may require a quantum description of gravity. In such a theory, spacetime itself could fluctuate, much as electromagnetic fields do. The vacuum would then not merely contain quantum activity, the fabric of distance and duration could become uncertain at the smallest scales. For now, the quiet between the stars is a reminder of how much reality can hide beneath appearances. The blackness behind a galaxy is not an empty curtain. It is a sea of fields, a stage for forces, and perhaps the source of the universe's accelerating future. So the next time you look into a clear night sky, remember that the darkness is doing more than separating the stars. It is participating in the cosmic story, carrying the fields that make matter possible and whispering clues about the laws we have not yet finished discovering. Empty space is not nothing. It is the lowest note of the universe, and beneath that quiet note, reality is still moving.